those. So given initial conditions P0 and Q0, the solution to PTQT is viewed as a parametric trajectory of a hypothetical particle at P0, Q0 times 0, and then it moves with some velocity P dot Q dot in that PQ plane. So the PQ plane is called the phase plane, and the path traced by this hypothetical particle moving is called the streamline. And the phase portrait is a graph of the possible streamlines in the phase plane depending upon that differential equation. A fixed point in the phase plane is where this velocity is 0. P dot derivatives are 0. P dot and Q dot are 0. So in this equation, we have a first order differential equation. P dot Q dot is A times PT QT plus B. A is a 2 by 2 matrix, B is 2 by 1. So we have 4 plus 2, 6 parameters. In the linear case, there are 3 possibilities for the phase portraits: node, saddle, and spiral. The center of the phase portrait is given by the fixed point. So if you set that to 0, P naught Q naught, and that will be minus A inverse B. The problem here is, given this derivative information, you want to find A and B. Those are the model parameters through some optimization procedure. Or given the PTQT, you find the A and B. So solving yields a linear combination of complex exponentials for PT and QT, whose exponents are given by the eigenvalues of A and the time variable T. So let me go there and show the picture. So a node is the case when the eigenvalues of that matrix A are real and of the same sign, and then there is a diverging pattern. These streamlines appear to go away from a fixed point or the origin or point of reference. When the eigenvalues are real of opposite sign, you get saddle, where you have this kind of a pattern. The streamlines are shown here. This is, at every pixel there is an orientation showing which way the particle would go. In the case of complex eigenvalues, you have a spiral. Now, in an image, there is no movement, there is nothing moving. So the direction is associated with direction of the fibroglandular tissue or whatever pattern you detect. And all of this is in a stationary image, fixed image. Here, these are functions of time. So we have to now switch and say, these are not functions of time anymore, but these are patterns in the image where the direction of flow P dot T, Q dot T will be interpreted or switched to the orientation patterns. And in the case of architectural distortion, we expect a node. Multiple spicules. These are like spicules. Lines going at various angles with a focal point. So a node is what is expected at the focal point of architectural distortion. We don't care about the other two. So by using phase portraits, we want to detect nodes that correspond to possibly multiple spicules coming out from a single point. But also it could be multiple ligaments, ducts, vessels that are overlapping and appear to intersect at one point in a mammogram due to projection. That is also possible. So Fabio used this for his, or developed his PhD thesis based on these concepts. The basic Gabor filter is the same, Gaussian, but we only use cosine. So it is a bit simpler to interpret now, a Gaussian modulated by a sinusoid. Previously, we had the J2 pi W put inside the exponential. Here it is shown separately. A set of 180 kernels was used with angles spaced equally, minus pi over 2 to plus pi over 2. It's getting tired. The projector is getting tired of my talk. So a few design considerations were put in. These are different from what you have seen for the other Gabor filters. So for this application, we said we want a line detector. We want the Gabor filter to detect lines of varying thickness and varying orientation and possibly varying length before the curvilinear structure changes orientation. So let tau be the thickness of the line detector. The parameters sigma x and f naught of the Gabor filter are related or are conceived as follows. The amplitude of the exponential term in that equation, the Gaussian term, is reduced to 1/2 of its maximum at x equal to tau over 2 and y equal to 0. So sigma x is tau divided by this scaling factor 2 square root 2 log 2. The cosine term has a period of tau, therefore f naught is 1 over tau. So we relate the modulating function period to the width of the line pattern we want to detect. The value of sigma y is sigma y equal to L times sigma x, where L determines the elongation or the oblong nature of the line pattern we want to detect. How long will a fiber be before it turns or changes direction? These are not straight lines. So, depending on the resolution of the image, we used a resolution of 200 micrometers. The large images were downsampled for the detection of architectural distortion. We're using fibroglandular tissues. We're not detecting microcalcifications. So we don't need 50 micrometer resolution. So 0.8 millimeter resolution at a pixel size, or this is tau equal to 4 means 0.8 millimeter at a pixel size of 200 micrometers, and L equal to 8 were used. So these are a few Gabor filters similar to what I showed earlier. This is a Gabor filter at some parameters. The Fourier transform is this. This is the Gaussian. As I was telling you earlier, each one is a Gaussian, but it's decaying slowly. You can see all the others. If you cut at 0.5, you will get an ellipse. If you stretch it, increase L, it becomes narrow. The pass band becomes narrower. If you make it thicker, it goes to the lower frequency band. If you rotate it, it rotates, that's all. So that is the effect of the design parameters. Okay. So the texture orientation was determined as the orientation of the Gabor filter that yielded the highest magnitude response. So in this case, we used 180 filters. We don't need 181 degree separation of filters. We could have done with 90 filters perhaps, but we left that optimization to later stages. We said at the beginning, let's just do 1 degree separation. So apply 180 Gabor filters at multiple scales if you want. And of all of those, what is the maximum response at this current pixel? Take that. And then what is the angle of the Gabor filter that gave you the maximum response? Keep that as the angle. So you form a magnitude response image and an angle response image for every pixel in the given image. So there is a magnitude response and the orientation field. Or the orientation field is a combination of the magnitude and angle at every pixel. So this is simply a representation. You are convolving the given image with a GK, that is the Gabor filter. The orientation is given by theta xy is alpha k max, where k max is the argument of the max of the fk xy, which are the responses of the k filters. But that's what I already said. Now, how do you characterize this with phase portraits? So let this delta xy be sin x, theta xy minus pi xy given a, b. You have found, you want to find a and b. There is an error. Sin xy minus pi xy given a, b. That is the error and you want to minimize that and find the A and B parameters that minimize this error. There is an angle field given to you, and there is an angle field of the orientation field of the model. You start with some AB, and it will give you that phase portrait, the angles. But from the mammogram, you have computed some angles. The two must match. And this is the error if they don't match. And modify A and B until they match, and find A and B. So for that, a nonlinear least squares algorithm was used. So for a given image, you compute three maps, three phase portrait maps. But you can't do this in one shot for the whole image. A mammogram has so many details. So you put a small, what is called analysis window, over a small portion of the mammogram, and do this analysis, phase portrait, find the phase portrait for that, and keep sliding the window and analyze the phase portrait. And create a node map for the entire image. So create three maps, slide the analysis window through the orientation field of the region of interest or the entire image. At each position of the window, determine the type of the phase portrait. Is it node, saddle, or spiral, based on the eigenvalues of A. Increment the value at the location of the fixed point. Fixed point is minus A inverse B. In the corresponding phase map, node, saddle, or spiral. We don't care for spiral, we don't care for saddle, so only one node map. If you want, you can create all of the others. The size of the analysis window was set as 44 by 44 pixels. In consultation with the radiologist as to what the size should be to capture the details. Let me go to the results here. The entropy of the phase map of HXY is again HXY over S. This is just a normalization factor times log of that. A map with dense spatial concentration of votes in the node map is expected to have a large maximum value and a low entropy. On the contrary, a map with a wide scatter of votes may be expected to have a low maximum and large entropy. The question is, we got a map. Is there one strong point where I can say that is a node? Or have the votes been cast at multiple different points? It's a scatter, so there is no real node. That is what we want to distinguish here. So for that, we use the entropy. So let me show application to a part of a mammogram. This is the part of the mammogram in the MIAS database that was marked as having architectural distortion. So when you apply Gabor filters, we get this. Clearly, you can see these fibroglandular tissues going in different directions. This way, that way, and so on. And that is the focal point, the center of that window, as marked in the database. These are the angles obtained for the Gabor filters. So when you have something here, you can see the angle there. When you have something there, you can see the angle there. They align. This is the node map. Saddle, spiral, there is nothing particular. Node map, there is something here. This is where we have a focal point. This is only for that part of the image. So this design is okay, at least in this basic image. So we did some analysis and with parts of images, and I'll skip all of that and let's go to a full image. The orientation field was filtered and downsampled. So we have this flow chart here. I'll skip all of that and go to the result here. So here's the full mammogram, and this is after initial pre-processing, some smoothing. You can see the smoothing there. And C is the orientation field. This is after filtering the orientation field. The orientation field that you estimate could have noise in the sense these angles may not be properly estimated. By filtering these angles, you see better alignment. And here, you see clearly a node point, meaning you have various directional components there. Elsewhere, you see the convergence of tissues going in a neatly ordered way. Not all of them, but you don't have such a pattern anywhere else. So the node map and the filtered node map, there is one large value there, but there are so many other large values. This is also a large value. So when we filtered the node map and put additional criteria, we reduced the node map to two large values. The details are there. You can read later if you wish. Filtering of the node map to remove scattered points by accumulating, like a Gaussian filter. Accumulate closely positioned values and build local peaks. Scattered values are rejected in the node map. So from this, we get this. So two large values, peak detection becomes easy. So detect peaks in the node map, and we got two, one there and one here. This is the area marked by the database. This is what we detected. We detected this also, but this is the nipple. And at the nipple, these structures must converge. So that is a partial node. There is nothing coming from outside, but these are all converging. So that is a point of convergence, and a node is a point of convergence or divergence, whichever way you see. Diverging, converging, we don't know if it is going this way or that way. There is no direction to 360 degrees, only 0 to 180. So this is a false positive, but it is understandable. So there is a technique known as free response receiving operating characteristics, like receiver operating characteristics or ROC analysis. But this is free response, which says, what is your sensitivity of detection of these points you want to detect in your database versus false positives? How many false positives will you put up to achieve that sensitivity? So by varying the cut point of some parameter, you can modify the sensitivity. That is, how many points can I mark on the image before I get the architectural distortion point correctly? Like throwing darts or putting pins. So I can close my eyes and put 1,000 pins per mammogram and I will get the correct answer. I'll find the point of architectural distortion, but there will be 999 false positives. That's useless. So if I put only one point, if the radiologist says, I allow you to mark only 1 point per image, then quite likely I'll miss many real points of architectural distortion. So then the question becomes, how many false positives can the radiologist tolerate and allow me to catch architectural distortion with higher and higher sensitivity? That is, how many real points of architectural distortion in the database will I detect? So if no false positive is allowed, my sensitivity is very poor. If 5 false positives are allowed per image, I get 55% sensitivity. So if I want 80% sensitivity or 90%, I have to put some 12 or 13 points per image. This is the initial stage of our research work on architectural distortion by Fabio Iris, which was 22 years ago, 2003 if I remember, 2004. Later on, Shantanu Bonik did some work on this and we got better results. I'll show you that in my seminar, perhaps on the last day. But this is how research work starts. At the beginning, you need to understand what the problem is and propose some methods. You may not get the best results, but still there is something worthwhile. There is a reasonable methodology. It is giving some results that are reasonable. There are limitations, yes, everything has limitations. But there is something interesting. Perhaps the idea is, pull this here, you want to go straight up and across. Or you want to go straight up 100% and no false positives. That is ideal. So you want this curve to go as shoot as straight as possible like that and stay at the top. So that is the goal. And we haven't reached that, but as I'll show you later on in Shantanu's work, we have come closer here. So that's the end of this chapter. We have seen that preferred orientation and directional distributions relate to the functional integrity of several types of tissues and organs. And changes in such patterns could indicate structural damage as well as recovery in the case of ligaments. Directional analysis could be used to study the health and well-being of a tissue or organ, as well as to follow the pathological and physiological processes related to injury, treatment, and healing. In the case of mammograms, it could assist in the detection of asymmetry and architectural distortion, two signs of breast cancer, two manifestations of breast cancer that were initially ignored in the early research on detection of breast cancer using mammograms. So that concludes the textbook material. I have gone fast, so we have more time to discuss or present some new results based on our research projects next week. And we will also have a few other lectures. Dr. Narasimhadhan is not here, but he is going to give a talk after our tea break now. And Dr. Shyam, what's his last name?
Shyam.
Dr. Shyam Lal will give a few lectures next week. 3 lectures?
The next week.
And how about you?
The next week.
Next week. Dr. Raghavendra also will give some lectures next week. I have indicated in the original plan that I'll give 3 seminars related to our research, totaling about 5 hours. But I think I'll take more and I'll add 1 or 2 more seminars. I may take 7, 8, 9 hours next week. And then I didn't know I would be finishing this today, but as you saw, I skipped some minor details. You don't need to know all the parameters of these equations that were used by my students then. Those are not important. The main idea is important. What was the methodology and what was the way of thinking in designing those methods? That should be enough. If you want minor details, they're there in the notes. If you want more details, go to the papers or the book. Or write to me, I can send you the papers. I can't send you the book because the copyright is with the publisher, but I can send you our research papers. Or you can find them. All libraries have access to IEEE and so on. Are there any questions?